Welcome back, MEFB 2132013 manufacturing processes. So, if you remember, we in the last class we spoke about electrical discharge machining. Okay, the anode, cathode, and when the potential difference is sufficiently high, then a spark is discharged, and every time a spark is discharged, material removal takes place. We spoke about electrochemical machining. Okay, electrochemical machining is the reverse of electroplating, where you have an anode and a cathode. So your workpiece is going to be placed in your anode because you want to remove material, and your cathode is made of tool, so it's all immersed in an electrolyte. Electrolyte is a current carrier, so when the circuit is complete, material will be removed from the anode, flow through the electrolyte, and deposited onto the cathode. Okay, so that in that way we have a mainframe to monitor material removal, because material removal is done in nanometer or micrometer range. Yeah? So we need a mainframe to monitor material removal. Then we spoke about laser beam and electron beam machining. So what is laser beam and what is electron beam? Laser beam, light, laser stands for light, amplification, simulation, emission, radiation, right? So laser uses the principle of light, where the light burns the material at a particular spot and machines it. Again, this is micro machining. And electron beam instead hits electrons on the surface of the object in order to machine it. Okay, so the major difference between laser and electron beam is laser is safer. Why? Because in laser beam machining we do not need we do not need to worry about the environment. It can be done in open environment because radiation is very minimal, or it's in the safe level, whereas electron beam machining has very high radiation similar to X-ray. Therefore, electron beam needs to be performed in a vacuum chamber. Yeah, so when you're doing electron beam machining, your object and your process needs to be conducted in a vacuum environment, and to create a vacuum environment, it is very costly. Therefore, we would consider electron beam machining, though it gives you the same results, but it's a more costly affair because we are doing it in a vacuum chamber. Okay, the next one for today is powder metallurgy. What is powder metallurgy? Powder metallurgy is the same concept as die casting. Okay, whereby in die casting, your metal is melted all the way to liquid. We call it molten metal. The molten metal will be poured into the mold, and then you are going to compact or pressurize it, and the final part will be ejected. Yeah, so you need to use hydraulic pressure, blah blah blah, to compact it at a temperature, or the sinter it at a particular temperature, and once sintered, you have your final finished product. Whereas powder metallurgy, the raw material comes in the form of powder, not liquid, but in the form of powder. Hot working, the raw material comes in the form of semi-solid metal. Okay, so in this case, powder metallurgy, the raw material comes in the form of metallic powders, and metallic powders is in nanometer range powders. So metallic powders are formed into parts by pressure and heat, which is sintering. Sintering is heating below the melting point temperature. What are the important characteristics of metal powders? Okay, first of all, the shape of the powder particle: spherical, flat, angular. The fineness, it refers to the particle size. Size is defined by passing the particles through standard sieves. Particle size distribution, it refers to the amount of each particle size in the powder, flowability, the ability of a powder to flow readily and to conform to the mold cavity, chemical properties, the existence of percentage of percentage of oxides, alloys and other chemical element which is defined. Compressibility, it is the ratio of the volume of the initial powder to the volume of the compressed part. Apparent density, it should be a constant so that the same amount of powder can be fed into the die cavity each time without any shortage or excess. So just like die casting, we need to feed in the right amount of quantity of material. Yeah, it's not like sand casting where the excess will fill up the gating system and blah blah blah. Here we need the exact amount. If the mold cavity needs 50 grams of powder, we feed in only 50 grams and powder, nothing more, nothing less. Yeah, so how does it work? So powder metallurgy. Okay, so if you look at it, yeah, powder metallurgy, you have your material in the form of powder. Again, we need to pour it through standard sieves, like how we did in the when we did, if you remember, we used the term standard sieves, yeah, in the die casting, right? So you're going to use a standard sieve to measure the size of your particles. Yeah, so you want to make sure you have nanometer range particles, so you're going to put this powder through a nanometer range sieve to ensure that your particle size is nanometer. So these powders are going to be mixed, so you're going to mix physically. Okay, you mix it physically. If you need iron oxide, so you're going to mix iron powder with iron sulfide. You're going to mix iron powder with sulfur powder physically, and then the mixed mixtures would be, it's physically only, yeah? So the mixed mixtures would be compacted. How you compact it? You're going to use a hand press. So you have a mold. Okay, the mold will determine the shape of your part. Okay, say your mold is round, so your shape of part is round. So you're going to pour in the powder into your mold, close the mold, and you're going to put the entire mold structure into the compaction machine. So if you look at this, this is your mold. Okay, your mold. You are going to this is your powder. Okay, this is your powder. So you're going to put it into your compression machine. Compression machine will compress it from top and bottom. Compress. So this powder would be compacted. Once powder is compacted, you open up the mold, and your part will be released. But if you must remember that this part is physically compacted, not chemically compacted. So once you're physically compacted, you have the shape. Okay, it's solid, but if you drop this down, it will shatter back into powder because it is not chemically compacted, it is physically compacted. Okay, so once compaction is done, the powder would be passed through a sintering process. Okay, so you see there's a sintering process. What is sintering process? Sintering is the same concept as heating above recrystallization temperature. So we are going to heat it up above, you're going to put the powder compact in there and heat it up above recrystallization temperature. Or we should say sintering is heating below melting point. Heating below melting point. So when you heat it up, if you heat it up at melting point, it's going to be liquid. So it defeats the purpose, right? So you heat it up below melting point is when you have the powder. Okay, you have the powder. When you heat it up below melting point, it is in a semi-solid state. The material has become soft and it starts to chemically bond, okay, within one another. So that's when you sinter it, And once you sinter, you will find that your specimen or your particle, just like coal or just like hot working, yeah, there'll be a reduction, there will be shrinkage, because initially when you compact it within the atom structure, there is voids, there is ruang kosong still present. But once you chemically or you sinter it, all the voids will be eliminated, and the atoms will chemically bond with one another. And lastly, you have your once it has sintered, you eject the part and you have your final finished product. Okay, so same concept, except the starting technique is different, where die casting uses liquid metal or molten metal, whereas powder metallurgy, your starting is a powder, okay, in the form of a powder. So again, the keyword here is micro. Your powder has to be micrometer or nanometer range fineness. So metals, powders to manufacture powders. So you have powder preparation, where you add your alloy or whatever into your main powder. Then you make your parts. Okay, you're going to put it into the mold. You compact it first, then you sinter it, and then your finishing operations, and you get your finished parts. Okay, there's two terms you see here. In the finishing operations, once the parts are completed, you need to improve the properties of the sintered powder metallurgy parts. How do you do it? Or you want to impart special characteristics, so you impregnation or infiltration. What is impregnation? Okay, so products like bearing are impregnated with oil by immersing them into heated oil. Why do you need to immerse bearing into heated oil? The oil will basically fill up the pores, so the bearing will have continuous supply of lubricant. For a bearing, you want it to move smoothly, yeah, without rubbing against each other. So by impregnating it with oil, it's going to have continuous supply of lubricant. Infiltration is the process of filling the pores of powder metallurgy parts by a molten metal to decrease the porosity. So what are the parts that you can produce? You can do coining. You can produce coining or coins. You can do a plating procedure. Okay, machining, heat treatment, all can be done on the final product. Yeah. Okay, so some products from powder metallurgy, or example of products produced by powder metallurgy: filters. Okay, where when you produce filters using powder metallurgy, you can obtain up to 97% of porosity. You can produce inserts, cemented carbide inserts. If you remember in machining, yeah, I told you that the most popular inserts will be high-speed steel and carbide. So these carbide inserts, which is widely used in manufacturing industries for cutting tools like tungsten carbide, cobalt, are produced using powder metallurgy technique. Gears, pumps, rotors which are made of iron and graphite, are also produced using powder metallurgy. Brushes for motors, copper and graphite, are produced with powder metallurgy. Bearings, copper, tin, graphite, are produced using powder metallurgy. And magnets are produced using powder metallurgy. Okay, so what are the advantages of powder metallurgy? Some metals that cannot be machined by cutting may be shaped by powder metallurgy. Okay, because like I mentioned to you, yeah, there are some difficult to machine metals because of its very high, very high toughness. Yeah, so you cannot grind the surface, you cannot machine it. So the best way to produce this kind of metals is using powder metallurgy, where you get it in the powder form. You mix it with its alloy, you compact it, and then you are going to sinter it. I can eliminate most of the machining, cutting, where you can obtain close tolerances. There is no metal losses. Okay, advantages of powder metallurgy: no metal losses. So because whatever you compact it in the form of powder into your mold is what you get. So you do not need to go and machine it excess, like how you do in sand casting and whatnot. Yeah, whatever you get is your perfect final finished product. You no need for skilled people. It's low labor cost. You get extreme pure products. You do not have impurities because you're using your powder, which is 99 or 100% purity, and there is large scale production. However, the disadvantages of powder metallurgy are difficult to machine because it is highly compacted, very high density. So your final product better be your final product. If you want to further machine it, it's going to be very difficult because it has the highest density. You have compacted it so well that all the pores, ruang kosong within the material has been removed. So you have a well dense structure, like I mentioned to you previously. Yeah, you have 98, 97, 98% of density, very, very dense. So it will be very hard to machine that kind of objects afterwards. So you must make sure that your powder metallurgy product is your final product. No more machining after that. Yeah, and it will involve high cost of equipment. You need a sintering furnace, you need a hand press to compact it. Yeah, metal powders are expensive and difficult to store. Yeah, so it is very difficult to store because powders can scatter. Yeah, and it may get oxidized, so you must store it with in a special container where you can control the humidity of the material of the powder. Okay, you do not want the powder to spoil. If the humidity is too high, the metal powder will get contaminated. Okay, sometimes intricate designs in products are difficult to attain because of the poor flowability of the particles during compacting. Some powders like aluminium, magnesium, titanium present explosive and fire hazards in a finely divided state. Some powders have thermal difficulties during sintering. Okay, what do you mean by thermal difficulties? That means during sintering, it may get oxidized or rust may form. Okay, and oxides may be produced during sintering. So all these are our challenges in powder metallurgy. So that ends the presentation. Thank you very much. I will see you in the next video. Bye. See you later in class. Yeah, please check your carry marks. If you are not satisfied, please let me know. If I'm missing anything, let me know. Thank you.